Fisch. I'm a PhD student at Stanford University. I'm also the chief scientist of Findora, and this is joint work with Alan Speniak, who's here in the audience, and Benedict Bunz. So the new result, the concrete new result, can be summarized as saying we have a SNARK with no trusted setup that for 128-bit security is about 10 kilobytes for a circuit of 1 million gates. And this is a significant improvement over what we knew before, at least before we wrote this paper, in terms of SNARKs with no trusted setup for a similar level of security and a similar number of, a similar complexity would be 200 to 600 kilobytes. And verification would be under 100 milliseconds. Take these numbers, however, with a grain of salt, because we have not implemented this scheme yet, unlike some of the other talks you heard today. This is new, and we'll be implementing it so we can get more accurate numbers. It's based on reasonable estimates, though, for the underlying. We can count the number of operations, and we can measure how we know how much the operations how much the operations should take. So asymptotically, the complexity of the SNARK, the size of the SNARK, as well as the verification time, scales like log n in the size of the circuit. This is hiding factors, constant factors that depend on the security parameter, so they're not actually constant. As the security parameter increases, so do those parameters. But the constants are comparable to the same constants that you would find on the other constructions in the space that have other terms dependent on the security parameter lambda. So the key new tool, however, is a polynomial commitment scheme using groups of unknown order. And this polynomial commitment scheme does not require a trusted setup when we instantiate the group of unknown order using this object called a class group. So if you look at a recent comparison, I'm taking this out of the Libre paper, just so that you can kind of see some numbers along the spectrum of different constructions. Still, the most efficient constructions are those that use a trusted setup per statement. Those are the Gross 16 SNARKs, or libsnark, and you still see that the verifier time and the prover time and the proof size is just so much lower than with any other construction. But when you move to the realm of no trusted setup, then you have things like so I'm not showing. So I guess I'm not showing here universal setup. So this is a little bit old. It does not include. I guess the Libre paper did not include comparisons for Planck and Sonic, etc. And I will have some other slides with numbers for that. If you look at the realm of specifically no trusted setup, then you have schemes which have efficient relatively efficient verification time, like libstark, but very large proof sizes. Or you have things like bullet proofs, which have pretty small proof sizes. You have 5.5 kilobytes. This was a computation, I think, involving about 15 million gates. But then an expensive verification time. And in bullet proofs, it's actually the verification time is linear in the circuit. So if you look at where Supersonic would fit in on this table, it would be about less than 10 kilobytes and less than 0.1 seconds in terms of verification. So I don't need to dwell on this, and I think it's something that everyone in this audience is familiar with. The motivation for moving to a trustless setup is that trusted setups, well, if they're subverted, then the prover can create fake proofs, and that might be done in an undetectable way, so you don't even know that fake proofs are being created. Even the fear that fake proofs are being created can cause problems, especially in the context of designing a currency. So it can be alleviated through distributed setup, but that's expensive and difficult, sometimes broken when you try to do it in practice. And there's low flexibility, especially if you have to do it once per functionality, which was the motivation for universal setup, which alleviates that a little. So just to review quickly, the key new tool that we're using is a new polynomial commitment scheme You saw in a previous slide a more formal presentation, just so you have the picture in your mind again. Polynomial commitment schemes allowed you to send the prover to send a small value that commits to the polynomial, and then later a verifier can ask for the opening of the polynomial at a point and obtain a small proof that the polynomial that was committed evaluates at the point z to some value y. And the commitment scheme can also tell you that the committed polynomial was of bounded degree. So Sonic was a SNARK system that was built using polynomial commitments. It had a one-time trusted setup for the polynomial commitment scheme itself, and that was improved in Planck and Marlin. Dark proofs offer you a different way of doing the polynomial commitment scheme using what we call Diophantine arguments of knowledge, because we represent the polynomial in terms of integers and then use homomorphic integer commitments using class groups, and then make arguments about integer relations in the exponent of the group. So I'll go through the details of some of the details of the construction, but the point is that we get log d communication in the proof and log d verification and no trusted setup. So we call our construction supersonic because it's sonic plus dark proofs gives you supersonic, but really the best numbers we get are when we plug in Planck instead of Sonic, which was an improvement of Sonic. And if you plug in Planck, then this is a slightly lower level of security. It uses 1200-bit class groups. So if you went to 128-bit security, it would be about 10 kilobytes, not 7.8. So we don't have specific estimates on the prover, but I'll tell you that it's about the same number of operations that are involved in SNARKs. But if you compare hash functions to class group operations, it's about 100 times slower. Right? So this is the kind of recent paradigm which the previous talks have gone over, of building taking an arithmetic circuit and turning it into this interactive proof involving polynomials, and then compiling that polynomial interactive oracle proof using polynomial commitments into an interactive argument, which is then turned into, finally, a non-interactive proof that would be a SNARK using Fiat-Shamir. So just to kind of review a bit more abstractly, polynomial IOPs are what are basically equivalent to algebraic holomorphic proofs, which you saw in Pratyush's talk on Marlin. But the idea is that basically in a polynomial IOP, the prover is sending a polynomial oracle in a box to, this is an abstraction, to the verifier, and then the verifier queries this oracle and gets the evaluation of the polynomial on points. And this could be made into a multi-round protocol where even in the pre-processing step, the prover and verifier have already established some polynomial oracles that can be queried at points, and in every round the verifier would ask the prover or send the prover a random challenge, and then the prover might send some more polynomials. The verifier can query those polynomials at points, etc., etc. And if you look at then how we build this to SNARKs, we apply a polynomial commitment scheme as a cryptographic compiler to take this abstract idea of a polynomial interactive oracle proof and make that very concrete. So every time you send a polynomial in a box, you're actually sending a small commitment to a polynomial, and every time the verifier is querying that polynomial in a box at points, the prover is supplying it with the answer and with proofs for those answers. So that's how you go from a polynomial IOP to an interactive proof with succinct communication, and then applying the Fiat-Shamir paradigm, you can transform this into a SNARK. So this is a similar theorem to the one that showed in Marlin. It says that any honest verifier zero-knowledge polynomial IOP, you can compile into an honest verifier zero-knowledge interactive argument of knowledge using polynomial commitments. So if you can summarize the key contributions in Sonic and Marlin and Planck, you get different polynomial IOPs. In Sonic, you basically get a 5-round polynomial IOP with 39 univariate oracle queries at 12 distinct points. The number of distinct points is very important for our compiler. And another interesting point is that different polynomial commitments may perform better or worse on different characteristics of the underlying polynomial IOP. So for us, minimizing the number of distinct points at the expense of having more oracles is actually good, which is why Plonk is particularly good for us, because this has a 3-round polynomial IOP where the total number of distinct query points is just 2. And Marlin has a different polynomial IOP. And so another thing that's being hidden is each of these are compiling circuits with where you measure the complexity slightly differently. So Sonic was multiplicative complexity, Plonk was arithmetic complexity, Marlin is R1CS complexity. So it's important to consider as well. What computation are you starting with, and how is it represented? So anyways, if you look at how if we apply the dark polynomial commitment scheme, which I'll describe, to different polynomial IOPs as the underlying information theoretic component, then if we plug in Sonic, we get something which is about 15.3 kilobytes. For Plonk, 10.1 kilobytes, and for Marlin, 12.3 kilobytes. This is estimated again for a computation with where we set n to be 1 million, but with Sonic, Plonk, and Marlin, in Marlin this would be the R1CS complexity is 1 million, and Plonk it's the arithmetic complexity, and with Sonic it would be the multiplicative complexity. So slight differences. If we compare how just this polynomial commitment compiler works to other polynomial commitment compilers, then this just contains the asymptotics. Based on pairings, you get the smallest proof size and verification time. It's basically constant, right? Or it depends only on the cost of performing group operations, so it's just dependent on the security parameter. But that's not transparent. It doesn't. It requires a trusted setup, which is why when you build SNARKs with it, you get SNARKs with universal setup. If you compare dark to previous constructions of polynomial commitments without trusted setup, then you see a comparison that if you look at the proof size compared to FRI, which you can kind of view as a polynomial commitment, the complexity is log d instead of log squared d. So that's why we get a size improvement over the works that use FRI to build transparent SNARKs. And if you compare it to what you would get if you use bullet proofs, with bullet proofs you get asymptotically about the same size in terms of the proofs, the openings of the polynomial commitments at points, but the verifier time is much, much worse. So the verifier time is linear in D. If you set mu equals 1, it's a univariate polynomial, so that would be O of D. And for us, it would be scaling like log D. There's also there's also one which is in between, which has a square root size argument, and there you get square root of D size proof size and square root of D verification time. So comparing it to other, again, like monolithic constructions of SNARKs, it's better to really compare the underlying components. And I think the theme that's coming out from all these talks is that all these constructions contain similar reusable components, and they can be mixed and matched to get different results. But if you look at Supersonic, which is combining the IOP from Plonk together with the dark compiler, then this is what you get. So in terms of proof size, it's much bigger than what you would get with Plonk or Gross-16, but those require trusted setups. And compared to bullet proofs, it's larger proof size, but much better verification time. And compared to Stark, it's a comparable verification time, but a significantly smaller proof size. So the main construction ideas are as follows. So we start with a polynomial over a finite field, and we build an integer encoding of that polynomial. So First, represent the polynomial as an integer, as a polynomial with integer coefficients, where each coefficient is in the range 0 to p. Okay. Then choose an integer q, which is greater than p, and output your encoding, which is the evaluation of this integer polynomial f at the point q. So we haven't done anything to reduce the size. We haven't built a compressed representation of the polynomial. This is not a polynomial commitment scheme. This is just an integer encoding that we'll use as a building block. So giving a small example here, if I had p equals 5, and this was my polynomial, then if I evaluated it at 10, I get 4,213. So why is this an encoding? Well, fact one is just that you could take the base q decomposition of the integer and you get back the coefficients of the polynomial, right? So you can always write an integer in terms of a formal sum of powers of q with the coefficients less than q, and you can recover back those coefficients uniquely doing the base q decomposition. Unfortunately, that is not enough for us, an artifact of the construction and proving security. You require an encoding that allows some of the coefficients to be negative. So the fact 2, which is the one we actually use, is that every integer in this range, negative q to the d plus 1 over 2 to q to the d plus 1 over 2, can be uniquely decodable to an integer polynomial. And if you can uniquely decode an integer polynomial, then you also uniquely decode a polynomial over fp of x just by reducing the coefficients mod p. And so it's uniquely decodable to a polynomial with coefficients of absolute value less than q over 2. Meaning if you started with a polynomial whose coefficients were bounded by q over 2 in absolute value, and you encoded it in this way, then you could get back the unique thing that you started with. If you started with a polynomial with larger coefficients, you wouldn't necessarily get back something unique. So steps 2 is to observe that there are certain homomorphic properties of this encoding. If we add 2 encodings together, then we get an encoding of the sum of the underlying polynomials, so long as q is sufficiently large. So in order to do homomorphic operations, we need q not to just be bigger than p, okay? Because then the coefficients, when you add them together, they will overflow q, so that they will no longer be bounded by q. But if you start, say, with q, which is greater than 2 times p, then you can add 2 together, and it's a valid encoding of the sum of the original polynomials. There's also this monomial homomorphism, where if you multiply the encoding f of q by q to the k, then you get the encoding of x to the k times f of x. And those are the properties that we use to build our polynomial commitment scheme. So in particular, if you have another way of constructing something with these properties, then you might be able to also construct a different polynomial commitment scheme that uses other assumptions. So we use groups of unknown order to build this. We build an integer commitment scheme using groups of unknown order. And notice that in a group of unknown order, in a group you have the map that if you have g to the x and g to the y, then you multiply them together, you get g to the x plus y. So we commit to the representation of the integer representation of the polynomial by sticking it in the exponent of a group element. So class groups are this thing built from the quadratic number fields. And basically, the size of a class group element is about the size of the discriminant. And if you start with a 1200-bit discriminant, then you get about 100 bits of security based on current estimations. It's about equivalent to 2048-bit RSA. So 1200-bit class groups would be like 2048-bit RSA. And they don't require a trusted setup to build. We can just choose a random discriminant and then define the class group. And it's believed that it's hard to find the size. So the evaluation protocol, information theoretically or abstractly, is like this. You start with the original polynomial f of x. You split it up into a left side and a right side, okay? Where the left side and the right side are both now degree d over 2. So you have fl of x plus x to the d over 2 times fr of x. So fl has all the left side coefficients. Fr has all the right side coefficients. But we factored out a term of size x to the d over 2, so the degree of fr is now half. And then the verifier sends a random challenge to the prover, and we recurse the protocol on the linear combination of the left side and the right side. So this becomes f prime of x, which is a polynomial of degree d over 2. And we recurse the same protocol on this, and in every step we reduce the degree by half. So what we actually do is we put those polynomials in the exponent of a group element, so that's how we get succinctness. And we send a commitment to the left side and a commitment to the right side. And so how does the verifier check that all these things are being done correctly? Well, the prover, because of the homomorphic properties of the commitment, the verifier could just check that the left commitment CL times the right commitment raised to the power q to the d over 2 is equal to the commitment that we started with at the beginning. And as well, the prover will supply the claimed evaluations of the polynomial at points. So he claims that the polynomial evaluated at z is equal to y. Then he'll give a claimed evaluation for the left part to yl, a claimed evaluation to the right part to yr. And this has to satisfy this consistency check that the claimed thing for the original polynomial is equal to the left part plus the right part times z to the q to the d over 2. Right? The problem is the verifier can't actually perform this check CL times CR to the q to the d over 2 efficiently. So instead of doing that, we use a trick called a proof of exponentiation. And it's the same trick used to build efficient VDFs. So the prover will prove that CR to the q to the d over 2 is equal to C over CL. And the verifier can verify this proof just doing two 128-bit group exponentiations, plus some other work but this is really the bottleneck of the verification. So at every step, the prover does two exponentiations, and we have a logarithmic number of steps. So we have basically 2 log of d exponentiations is the total verification work. And in addition, observe in terms of what we're actually sending, we're just sending, and there's some optimizations we can make, so you only send 2 group elements per round. So we get 2 log d proof size, 2 log d exponentiations for verification. So the last thing is that the problem is that the coefficients are growing in each round because we multiplied the right side by a factor alpha. So that's why we can't actually just set q to be larger than p, but we have to set it to be basically larger than p to the 2 log d. So the last final step of recursion, the verifier is just sent a polynomial of degree 0, which is just a constant term. And the verifier is given this constant term in the clear and can just check this directly. Now, I haven't explained zero knowledge. What I've described so far is not zero knowledge at all. But we have a way of transforming this using kind of standard tricks into zero knowledge by doing things over hiding commitments. Thank you, and I'll take some questions.
Is there any questions?
Hi, Ben. Great talk.
Thank you.
I had a question. So what about this is specific to groups of unknown order? Could you not do this over like a
integer commitments, right. So if you have another way of building a homomorphic integer commitment scheme that also, so if you have another, basically if you have another way of building a homomorphic integer commitment scheme, then you don't need to use groups of unknown order. But you have to, it has to also have succinct openings, right?
So basically you have to ensure that you don't wrap around mod q.
Right, right.
Okay.
So this is really the reason for using groups of unknown order is that you can prove relations about integers in the exponent because you can't reduce the equation in the exponent modulo anything.
Okay.